Hi everyone, I'm Dr. An. This is the third tutorial where we discuss text augmentation and its applications on natural language processing. Data augmentation techniques are used to generate additional synthetic data using data you have. Image augmentation has been widely used in computer vision applications, whereas text augmentation is relatively new to natural language processing field. The nlpaug module implements a number of high-performance text augmentation algorithms that may boost performance of NLP models. In part 1 of this tutorial, we introduce some cool text augmentation functions in the nlpaug module. In part 2 of the tutorial, we use the nlpaug module to generate text augmentations to Twitter tweet data and evaluate back-of-words model performances with and without text augmentations. In this part 3 of the tutorial, we will use the nlpaug module to generate text augmentations to Twitter data and evaluate deep neural network model performances with and without text augmentation. Let's get started. First, you need to install and import some modules. Here we installed the GenSam module, and we also import the module, making sure that we utilize the most recent version of the GenSam, which is 4.20. We also install some additional modules, including the tokenizer, which is needed by the back translation model. And of course, we need to install and import the nlpaug module and its various methods. And we also install the Hugging Face transformers because we are going to utilize the NLP models from the transformer. And we install the data sets. Also, we import other modules, including ALTK, Pandas, NumPy, and some matrix functions from scikit-learn and transformers. You need to mount your Google Drive to Google Colab in order to use the files stored in your Google Drive. Again, as in the second part of the tutorial, we are going to use the Twitter climate change sentiment dataset, which you can download from Kaggle following this link. So the Twitter climate change sentiment dataset is a dataset that was funded and collected by Academia Foundation for Innovation, JFLF grant to Chris Bouch at University of Waterloo. And the dataset aggregates tweets pertaining to climate change collected between April 2015 to February 2018. There are a total of 43,943 tweets which were annotated. Each tweet is labeled independently by 3 reviewers, and the dataset only contains tweets that all 3 reviewers agreed on. And each tweet is labeled as one of the following 4 classes. 2 denotes news. The tweets links to factual news about climate change. 1 denotes pro, meaning the tweet supports the belief of man-made climate change. 0 denotes neutral, means the tweet neither supports nor refutes the belief of man-made climate change. And -1 denotes anti, means the tweet does not believe in man-made climate change. You can read in the dataset using Pandas, using the Pandas read CSV function. And then you can rename the column names and remove some unused columns. An important step is to recode the labels. Previously, the labels were -1, 0, 1, and 2, but for Hugging Face classification model head, its preferred labeling convention is from 0 and with an increment of 1. So therefore, we replaced the original values of -1, 0, 1, and 2 to consecutive values 0, 1, 2, and 3. So that 0 now denotes negative sentiment, 1 denotes neutral, 2 denotes positive, and 3 denotes link to news. We also want to drop any missing values so that the missing values would not deter the training progress. And we use the scikit-learn train test split function to split the data into 80% of training data, 10% validation data, and 10% of test data, so that we have about 35,000 in the train set, about 4,400 in both the validation and the test set. We convert the 3 data frames, the 3 train sets, into the Apache Arrow format, which is the data format used by Hugging Face transformer models. We use the dataset from Pandas to do the conversion. And after that, we will use the dataset dictionary function to gather the train, validation, and test datasets into a single dataset dictionary, which can be manipulated together. And we will call this dataset dictionary tweets. And you can take a look of the generated dataset dictionary object, which contains the 3 datasets we created, one for train, one for validation, and one for test. And for each dataset, it has 2 features. One is label, one is corresponding tweet text. Then we can decide what model we want to use for the Twitter tweet classification task. Here we use one pre-trained model from Hugging Face called Distill, BERT, Base, and Cased. And we specify the model checkpoint, and then we can load the tokenizer from the trained model using the auto tokenizer from pre-trained method. And then the tokenizer corresponding to the Distill, BERT, Base, and Cased model will be downloaded automatically. And now we can use the tokenizer to tokenize the whole dataset. So to tokenize the whole corpus, we will use the map function of our dataset dictionary object. The map function provides a convenient way to apply a processing function to each element in the dataset. At the first stage, we first define a processing function to tokenize a batch of examples. And we use padding equals true so that the shorter tweets after tokenization will be padded with zeros so that all the length of different tokenized tweets in a batch would be the same. And then we also specify truncation equals true so that we can truncate examples to the model's maximum context size, which is 512 tokens for the BERT model. After that, we can apply the map function on the dataset dictionary object tweets, and we use the tokenize function we defined. We specify batched equals true so that the map function is going to process the dataset dictionary object in batches. And we further specify batch size equals none, meaning that the map function is going to tokenize the entire dataset as a single batch. This would ensure that the input tensors and attention masks to have the same shape globally for all the observations. Alternatively, we could also specify max length argument in the tokenized function to ensure the same length of the tokenized tweets globally. After applying the map function, we can take a look of the encoded tweets. And as you can see, besides the label and the text for each of the three data sets, the train, validation, and the test data sets, in the dataset dictionary, we also have two other columns, the input IDs and attention mask, which are generated by the tokenization. And the input ID and attention mask together with label are going to be used by the NLP model, the BERT model later on. We can remove the text column because the model will not utilize this column anymore. And we also need to convert the input IDs and attention mask columns to the PyTorch format, which is required by Hugging Face transformers. We use the set format function and specify torch with the corresponding columns. So those columns data will be converted to PyTorch format. Now we can load the pre-trained model. The first thing we need is a pre-trained distill BERT model. And we use the auto model for sequence classification model instead of the auto model in the Hugging Face transformers. So the difference between the auto model for sequence classification model is that it has a classification head on top of the pre-trained model outputs, which can be easily trained with the base model. We just need to specify the number of labels the model has to predict, and we have 4 labels, basically 4 sentiments to predict in our case. And the number of labels is going to dictate the number of outputs the classification head has. We use GPU for model training, so therefore we determine the availability of GPU, and if GPU is available, we will assign that to our device. We'll define 2 dictionaries that convert IDs, basically 0, 1, 2, and 3, and labels, which are strings. And we'll add 2 functions. One function is converting label to ID. The other is converting ID to label. And for labels, we specify there are 4 labels, the anti, neutral, pro, and news. And then we can easily create these 2 dictionaries, converting label to ID and converting ID to label, which will be used in the model training process. We can take a look of these 2 dictionaries after their creation to make sure they are correctly specified. And now we can grab the pre-trained model with a classification head by specifying auto model for sequence classification from pre-trained. And we specify the checkpoint for the distribute BERT and encased model. And we also provide the 2 dictionaries, the label to ID dictionary for both the label to ID dictionary as well as the ID to label dictionary. And also we need to tell the number of classes or labels, and there are 4 of them indicated by the length of the dictionary. And also remember that we need to move the model to the GPU so that training can take place in the GPU. Then we need to define the performance matrices to monitor matrices during training, we'll need to define using the compute matrix function for the trainer. And because we are doing a tweet classification problem with multiple categories, we are going to compute both the F1 score as well as the accuracy of the model. And we define the function to compute these two matrices. And the compute matrix function take an argument of predicted label, and then we compare the predicted label to the true label. And we include both predicted and true ground truth labels in the F1 score function as well as the accuracy score function in scikit-learn so that the F1 and accuracy scores can be calculated. Now we can train the model. To define the training parameters using Hugging Face models, we can use the training arguments class. So this class stores a lot of information, and you can use the arguments to gain fine control over the training and evaluation process. And here we specify the batch size and the number of epochs we want to train the model. And you can also name the model using the model checkpoint and then whatever you want to specify. Here we specify the name of the model as model checkpoint and then fine-tune climate change because we are using the distributed model and fine-tune it to classify climate change related sentiments in tweets. We can specify the path where to store the fine-tuned model. And then we can utilize the training arguments. Here we specify the path for the output, where to save the model. And we specify the number of training epochs, the learning rate, and also the batch size for both training and validation. We want some L2 regularization, so we specify weight decay equals 0.01. And we want to evaluate the model every epoch. And also we want to load the best model at the end. After model training, we don't want to push the model to hub because that's going to take some time. So we specify push to hub equals false. And finally, we want to save checkpoint after each epoch of training. After specifying the training arguments, we can define the trainer. And in the arguments, we specify the model, the training arguments, and the evaluation metrics, basically F1 score and accuracy. And also we specify the train data set as well as the evaluation data set, and finally our tokenizer. Before the training, optionally, you can clean up the memory using the garbage cleaner, gc.collect, and also you may choose to empty the cache in CUDA so that you can release some additional memory for the training. And now you can start the training process, just call the train method on the trainer. And after training, you can take a look of the results. The model was trained for 3 epochs, and we see that the training loss is reduced for 3 epochs. And then the validation loss also reduces, although less dramatically. And you also see that we get the accuracy F1 score calculated for the validation set. And so the highest accuracy the model achieved is 0.773555, and the highest F1 score achieved by the model is 0.767816. And now you can take a more detailed look at the training matrix by calculating the confusion matrix. And then you can also visualize the confusion matrix first we need to get the predictions on the validation set using the trained model. The predictor method of the training class returns some useful object we can use for evaluation. So here we first use the predict method to predict the sentiments of the validation set using the trained model. And after that, you can take a look of the metrics, basically the accuracy score, the F1 score, as well as loss and other metrics of the predicted output. And as you can see, the accuracy again is 0.77355, and the highest F1 score is 0.7678. You can also get the raw predictions for each class using the NP augment function. And with the raw predictions, you can plot the confusion matrix using the confusion matrix command. And then you can display the confusion matrix using confusion matrix display function. And the confusion matrix looks like this. On the y-axis, you have the true label of anti, neutral, pro, and news. And on the x-axis, you have predicted label, so that you can take a look of the model predictions for each of the 4 categories. You can also make predictions and take a look of the model performance on your test set following the very same procedure. As you can see on the test set, the model gains a highest accuracy of 0.7782 and an F1 score of 0.7715. You can save and share the model using the save pre-trained command. You want to save both the model as well as the corresponding tokenizer so that later on you can create a pipeline to use the fine-tuned model. And this is the way that you can utilize the model that is fine-tuned and saved. You can create a pipeline and utilize the model as well as the corresponding tokenizer. You can assign that to a classifier. And then say here we want to test the pipeline with a sample tweet. The custom tweet is stop dumping trash and save our ocean. And you provide the sample tweet into the classifier, and the classifier is going to make a prediction. And the prediction that has the highest score or highest probability is pro, meaning that the model classify the sample tweets as positive, basically supporting climate change theory. You can test another tweet. Here I specify global warming is a fake claim made by some crazy scientist. If you use the model to make a prediction, the model produces a very high score for anti, suggesting that this tweet possibly is anti-climate change theory. Now we can test using the text augmentation strategy and see whether the text augmentation will be able to improve the F1 score and accuracy of the model. We especially initiate 3 alternative text augmentation strategies. The first strategy is the synonym augmentation. We use the synonym aug command from the NLP aug module, and we maximally want to replace the orange tweet words with up to 3 alternative words which are synonym to the words it wants to replace. And the second strategy for text augmentation is the contextual word embeddings. And in this case, we are going to use the contextual word embedding aug in the NLP aug module to create contextual word embeddings, and we are going to use the model DistillBird based encased to generate the word embeddings. And we are going to choose the action of substitute, basically substituting the token in a tweet with the model prediction. And to accelerate the creation of contextual word embeddings, we are going to utilize GPU. And the third type of text augmentation is called back translation. So basically, we want to use the back translation aug function in NLP aug module to first translate a tweet from English to German, and then we want to convert the translated tweet back into English. And through this exercise, and hopefully some of the tweet's contents are going to be changed incrementally so that we can create some alternative tweets based on the original tweets without substantially change the original tweet's sentiments or meaning. Again, we are going to utilize the GPU whenever available because otherwise the back translation arc is going to take for a really long time. And now, as a final step, we need to create a function to evaluate text augmentation on model performances on the test set. The function is called evaluate_arg, and it allows you to specify what one of the three text augmentation strategies we just specified, and alternatively, and also you can specify the number of tweets, augmented tweets you want to create for each original tweet. So if you set n equals 2, it means that for every original tweet, you are going to create 2 text augmented tweets. And you also need to supply the twin set and also the validation set and also the test set. Here we create 2 lists to store the augmented tweets and their corresponding values. And we can loop through the twin set to create augmented tweets. Here we loop through each observation in the twin set. And depending on your specified text augmentation strategy, we can use a synonym-based strategy or word embedding-based strategy, or alternatively, the back translation strategy. And then we append the augmented text to the list of augmented tweets and also corresponding labels to the list of augmented tweets labels. And we can zip the 2 lists into a list of tuples and then convert the list of tuples to a Pandas data frame. So this df augmented twist labels is going to be a data frame containing all the augmented text augmentation generated tweets and corresponding labels. And then we can vertically stack or concatenate the twin set with the augmented text using the Pandas concat function. And then we can convert the overall data frame to a data set in the Apache Arrow format, which can be consumed by Hugging Face models using the dataset from Pandas function. After that, we can gather the augmented training set together with validation and a test data set to form a single dataset dictionary, which can be manipulated together. We'll call it tweets augmented. And then we can tokenize the twist datasets together using the map function. We can remove the text column from the encoded dataset dictionary because the model does not use it anymore. And we also need to convert the 3 columns, the input IDs, the attention mask, which were created by the tokenization process, as well as the label column, into PyTorch format, which can be consumed by Hugging Face transformer models. After that, we can just use the trainer. We specify the model, corresponding training arguments, the metrics for evaluation, basically F1 score and accuracy, and also specifying the training and validation set, the tokenizer. You can optionally clean up the memory using the garbage cleaner, and then you can start the training process using the .train method. And after model is trained, you can use the model to predict the test set using the predict function, and then optionally report the matrix evaluation on the test set. And now let's take a look of how well the synonym text augmentation performance is. We can initiate the evaluate org function we created above, and we specify augmentation strategy as synonym. For every tweet, we just create one text augmented tweet. And then we provide the train, validation, and the test set. And let's take a look of the modeling results after text augmentation using the synonym strategy. As you can see, the training loss reduces dramatically for the 3 epochs, whereas the validation loss actually increases, suggesting possibility of overfitting. In terms of the accuracy, actually the first epoch has the highest accuracy, as well as the highest highest F1 score on the validation set. The accuracy at F1 score, if you compare them to the corresponding highest accuracy and F1 score without text augmentation, we will see roughly about 1% gain in accuracy F1 score following text augmentation using the synonym strategy. So the synonym strategy in this case marginally improved the model performance, at least on the validation data set. And we can also take a look of the text augmentation performance on the test set. And as you can see, the accuracy of the text augmented NLP model also have about a 1 percentage point increase in accuracy as well as F1 score on the test data. Now let's evaluate the second text augmentation strategy, the word embedding. And we specify the augmentation strategy as embedding. And as you can see, after training the model for 3 epochs, again, we see a reduction in training loss. And on the other hand, the validation loss tend to increase over epochs, suggesting overfitting. And also, we get the highest accuracy at F1 score on the validation set in the very first epoch, about 0.789 for the accuracy and 0.782 for the F1 score, which again is about 1 percentage point higher than the model without text augmentation. And we see similar results and actually a little bit even higher accuracy on the test set. And finally, we evaluate the back translation text augmentation. We specify augmentation strategy as back translation. And again, we see very similar patterns. The training loss reduces dramatically over 3 epochs, whereas the validation loss tend to increase, suggesting overfitting. And we achieve the highest accuracy and F1 score on the validation set in the epoch 3, the very last epoch. The accuracy is 0.7883, and F1 score on the validation set is 0.7858. Again, that is about 1 percentage point higher than than without text augmentation. And we see very similar results in terms of accuracy and F1 score on the test set. So our conclusion is that after doing all three types of text augmentation strategies, we find that in general, all three works equally well on the validation and the test set, and we gain about 1 percentage point of accuracy at F1 score in comparison to not having text augmentation at all. So this concludes the third and the very last tutorial on text augmentation. Thank you so much, and see you next time.